Then what is the history of this information and where it's coming from? The content definition is coming from the scientific community through the Galileo Scientific Advisory Committee and IGS. IGS in the 2011 requested to the European Commission a subset of information that was needed for PLD. Then this was acknowledged, and from 2011 started the distribution of for IOB of the center of mass through IRS website, and from 2016 start the full set of information for IOB, but for all the Fox satellites that were later launched. And this information is maintained, not only the static. Each time there is a change of mass, there is a new set of information on the two websites. Then, what was the content that IGS requested at the time to the project? They requested a subset of information that this was frame, center of mass, navigation antenna, laser location, altitude, geometry, and hardware delays. If we take this original list of information, this can be divided in three main areas. We have the areas of vectors and orientation in the space, and information required on the geometry for the solar radiation pressure model, and finally for the hardware delays for multi-frequency user. I will shortly describe where is coming from each set of information that we can understand what is being released. First, it is the mass and center of mass. For the mass, each satellite is provided with the exact mass that has been measured and the position of the center of mass. And that is provided in the satellite body frame. Where is coming from this information? This is coming from the individual measurement of each satellite in the bench. We can see here, for example, a Fox satellite being measured in Este, in the Netherlands. This is done in flight configuration. Everything that was not supposed to be inside is removed and is done on a stock configuration and without propellant. Then this is not the flight configuration. The satellite is later moved to Kourou. It is filled with propellant, and the flight configuration is derived knowing the exact amount of propellant that has been loaded to the spacecraft. This information is maintained. We can see here, for example, what is the X direction of the Fox satellite. We can see that satellite 201 and 202 that are in the eccentric orbit. They have almost the complete time to circularize the orbit, and the X value, it is a little bit away from the other Fox satellites, as well as the mass. Then for each satellite, after each maneuver and launch, we have accurate values for the center of mass. Next set of information, it is what is located the navigation antenna. The navigation antenna, it is based on three vectors. The first is the antenna reference point. This is a fixed vector per satellite family. It's a mechanical point on the satellite body frame. Then we have the navigation antenna. For the navigation antenna, we have phase center offset and phase center variations. They are provided on the website through a dedicated link to an text file. They are on the satellite body frame referred to the antenna reference point. That is different to IGS. Where is coming from this information? It is coming from the individual calibration of each navigation antenna. And in the file, we have the phase center offset, but also the variation in azimuth and in zenith for IUB from 0 to 14, but for FOG, this was extended to cover also LEO satellite up to 20 degrees. The next set of information is the laser reflector. This is per satellite family. We have the position of the optical center of the retroreflector on the satellite body frame. We have here the values for IOB and fog. We can see here the retroreflector panel from fog. These pictures are quite uncommon to see the retroreflector visible in the picture. Then the next is the attitude. The attitude, we have the nominal low, that is the green one. We can see here a U-turn. And during eclipse, this attitude low cannot be followed because the satellite cannot rotate as quick as the green line. Then there is a modified yaw. You can find the equations on the website, and we can see here how the blue line and the reverse PPP estimations done by my colleague Florian Disner follow quite well the modified law. That means this law is quite accurate and can be used for POD. This is in the area of positions of the points and the vector and the orientation. The next area is the geometry of the satellite. This is important for solar radiation pressure model use of box-wing model. There is one area of the website that are the satellite dimensions and the optical properties. For example, we can see here the plus Z surface of the satellite has been divided into main materials, the MLI, multi-layer insulation, material A, and the single layer insulation, germanium cadmium, material B. And finally are the hardware delays that are important for linking the different frequencies for multi-frequency user. This is coming from the calibration as well on ground for each satellite from the signal generation to the output of the navigation antenna. Then, why we are releasing this information and what is the scientific benefit? For the navigation antenna in 2011, one of the main benefit assumed was to use GNSS for the ITRF scale. This was one assumption. Then today, in 2023, the availability of these calibrations for Galileo has made possible for the first time to GNSS to contribute to the scale of the ITRF. For the latest ITRF 2020 generation, Galileo scale or GNSS scale was not yet considered to contribute, but there was a very good discussion and a good consistency with the BLBI scale. And hopefully in future this will lead to new advance in the scale. Then in the area of attitude and geometry, before the release of the model in 2016, box-wing and the modified yaw were certainly used for Galileo. After the release, box-wing model are now commonly used and most normally the baseline for derived POD products and genetic products. Conclusions. What are the metadata? They are the metadata, the relevant satellite properties required for precise orbit determination. This information is coming from the scientific community, it's not generated by the project, it's coming from IGS as well. It was from 2011, has been released, and it is maintained through the website. There is a benefit for this information. We can see that on the ITRF 2020 generation, and also on the box-wing, we can see that is very used in the POD determination of Galileo. Finally, I want to come back to feedback. Galileo was the first GNSS for which this information was made publicly available, thanks also to IGS. This was very difficult at the time. Now it will be relevant to have feedback from the IGS and provide feedback of how this is benefit for science and possible improvements. Besides ITRF, there could be also other improvements for benefits, for example, on the length of day, and it would be good to see the community using this information. And that concludes my presentation, and thanks for your attention.
Francisco, thank you very much for this, I would say, very interesting presentation. And I simply would like to really provide acknowledgement to Francisco, because he was very, very hard fighting from the early days related to the release of metadata. So he's a strong advocate for releasing the data and provide expertise and justification. So on that stage, I would like to use the opportunity to thank you very much for your dedication and the support you provided.
Thanks,
Especially
I
also
really appreciate it.
that we're really getting that out. So it was excellent. Thank you very much for that.